Okay, so we are live. Let me share my screen. Can someone confirm that you can see the screen?
Yes, sir.
Okay, thank you. So good morning. Today we are going to look at about the perfect secrecy. So I should just tell what we have done in the last class. We talked about discrete random variable. So discrete random variable, x bar consisting of a finite set x and a probability distribution associated with defined on x actually, right? And then we talked about conditional probability, joint probability, uh, you know, then we talked about perfect secrecy. So perfect secrecy, uh, you know, in fact, we talked about, so we then after that actually, before that actually we treated uh, plain text as a random variable, key space as a random variable and ciphertext as a random variable. Then we talked about perfect secrecy, saying that uh, basically Oscar can obtain no information about the plain text by observing the ciphertext. So I think I should show you we doing. So we talked about this discrete random variable, right? Then we talked about these are certain properties. We talked about joint probability, conditional probability, independent random variable, and this condition joint probability is basically product of corresponding probabilities. Okay, and we have then bias remains fine. Then we talked about perfect secrecy. Okay, so here is a crypto system has perfect secrecy if the condition probability x condition y is same thing as probability of x for every x in P and for every y in C. In fact, in other words, it's a probability that the plain text is x given that the ciphertext is or that the ciphertext y is observed is identical to the probability that the plain text is x. Okay, so this condition must be satisfied. Then we say that the crypto system is perfectly secure. Loosely, that means Oscar can obtain no information about the plain text by observing the ciphertext. After that, we have shown that shift cipher is perfectly secure, right? I think this was the last thing that we did. Uh, so now I will give you a characterization of uh, this perfect secrecy, uh, and this is especially when the size of plain text is same thing as size of ciphertext. Is same thing as size of key space. So let me build some ideas, and then we will give you the characterization. After that, we will talk about entropy of a random variable, and then we'll talk about entropy of our random variables of the crypto systems, right? Like P, K, and C, and then the relationship between them, and why entropy is quite useful. We'll talk about it. So, so now we are ready for this characterization of perfect secrecy. These are the ideas of Shannon. Okay, characterization of perfect secrecy. So let me build up a few ideas. If probability of x naught is 0 for some x naught in P plain text, okay, then we know that probability of x naught condition y is same thing as probability of x naught. So trivially true for every y in C, right? So we need only those plain text x in P such that probability of x is positive. So for such plain text, using Bayes' theorem, we can observe that conditional probability x, condition y equal to probability of x. This condition of perfect secrecy, probability of x condition y is same thing as probability of x for every y in C is equivalent to probability of y condition x equal to probability of y for every y in C, right? Therefore, we can assume that the probability of y is positive for every y in C. So if probability of y is 0, then ciphertext y is never used and can be omitted from C. Okay. So now fix any x in P, and then for each y in C, we have probability of y conditioned x is equal to probability of y positive. Okay. So for any x in P, for each y in C, we have probability of y condition x is equal to probability of y. This is positive, right? Because we have assumed that probability of y is positive, right, for every y in C. So that means this implies that for each y in C, there must be at least one key k such that ek of x is equal to y. This implies that size of k will be at least size of C. Now, in any crypto system, we know that size of ciphertext is more than the size of plain text, since each encoding rule is injective, because encoding rule is injective. Right? So these are some relationship. So now I can state the main result, the factorization. Suppose P, C, K, E, D is our crypto system, where size of K is same thing as size of C is same thing as size of P. So the plain text, ciphertext, and the keys have the same size. Then crypto system provides perfect secrecy if and only if every key is used with equal probability one divided by size of K, and for every x in P and for every y in C, there is a unique ek such that ek of x is equal to y. This is our main result. So we can prove it. So basically, if size of K is same thing as size of C and size of P, crypto system is perfectly secure if and only if every key is used with equal probability 1 by size of K. This is a very important result actually. So let me prove it for one side, and other side I will leave as an exercise for you. So let me do it. Suppose we are supposing. Suppose it provides perfect secrecy. Suppose it provides perfect secrecy, right? So then I will show you that the probability of key is 1 by k for every k in k, right? So now for every x in P, the plain text, and y in C, ciphertext, there must be at least one key k such that ek of x is equal to y, right? This implies that size of C is nothing but size of ek of x, thus that k belongs to k is less than or equal to size of k. But we know that size of C is same thing as size of k in our, that's a given condition. This implies that size of ek of x such that k belongs to k, capital K, is same thing as quantity of k. This implies that there does not exist two distinct keys k1 and k2 such that ek1 of x is equal to ek of 2, ek1 of x is equal to ek2 of x is equal to y. So remember, we are saying there is a unique, there is a unique key. First of all, I want to show that there is a unique key k, right? So this implies that there exists unique key k such that for any x in P and y in C, ek of x is equal to y. Right, so because of this size, we are able to show this. Now this is one part of it. Let n is equal to size of k, and let p is equal to xi, such that 1 less than or equal to I less than or equal to n. Of fix a ciphertext element y in C. Now name the keys as k1, k2. Where there are n keys, I can call them k1, k2, kn, such that eki of xi is equal to y. 1 less than or equal to I less than or equal to n. Right. Now, for each of these ki, I can actually now apply the Bayes theorem. I can compute this conditional probability x of I, each xi actually of y, and see what happens. So this conditional probability x of I condition y is same thing as, using Bayes theorem, probability of y conditioned xi, probability of xi divided by probability of y. Now this is same thing as probability of k bar is equal to ki, probability of xi divided by probability of y. Now, for perfect secrecy, it is given that the system is perfectly secure. We know that probability of xi condition y will be same thing as probability of xi, right? So I can use this. I can use it here, substitute it here. So this means we will get probability of ki is equal to probability of y. 1 less than or equal to I less than or equal to n, right? Because this, when you substitute here, this probability of xi will cancel out, right? So probability of k bar ki is equal to probability of y. In other words, probability of ki is equal to probability of y. This implies that all keys are used with equal probability, right? Which is probability of y. But since number of keys is size of k, this implies that probability of k equal to 1 over this for every k, right? So we arrive at this result. That means if this is a crypto system with this is equal size, so it's a perfectly secure. I have shown that every key is used with equal probability this for every x in p and for every y in c, and there is a unique key k such that kx equal to y. Reverse part I left, I will leave. You can try, or that's okay. So that's all about perfect secrecy. I think I just wanted to mention one more crypto system known as one-time pad, which is important crypto system. At one point of time, it was pretty useful. One-time pad. So it was given by Gilbert now in 1917. So if you are using it without knowing that it's a perfectly secure, later on it was shown that it's perfectly secure. So this is that if n is a positive integer greater than or equal to 1, and suppose p is equal to k is equal to c is equal to z2 raised to power n. Okay. So for k in z2 raised to power n, we define x is equal to x1, x2, xn, y is equal, and sorry, k is equal to k1, k2, kn, ek of x, our encoding rule, x1 plus k1, xn plus kn, mod 2. And if y is y1, y2, yn, suppose the resultant is y1, y2, yn, then decryption rule dk of y is equal to y1 plus k1, yn plus kn. Why there is a plus sign? Because actually it's a modulo 2, so plus 1 is same thing as minus 1, right? So these OTP one-time pads provides perfect security, provides perfect secrecy. And so they are unconditionally secure. Okay. Now there is one disadvantage of OTP, that size of k is more than size of p, plain text. So amount of key is as big as plain text, right? So OTP is vulnerable to known plain text attack, but they are OTP one time pad. So that's all about one time pad. Now I think we are ready for the entropy. So I think we talked about. I'm again reiterating what we have done. We talked about discrete random variable x bar, which is a finite set x and a probability distribution of x, right? Now I am going to basically compute the entropy of x bar. So entropy is a thermodynamic quantity you might have heard in physics, and later on those ideas were extended to basically in the information theory domain by Shannon. So I am going to talk about entropy of a random variable. Okay, that's very important concept. So let me motivate you with some basic ideas. Then I will give you the definition of entropy of a random variable. And then we'll compute entropy for our crypto system. Okay, and these are very important ideas. So we may discover a crypto system, but then we can analyze them using these probabilistic ideas and the ideas of entropy, and then we know ahead of time that how they are going to behave, right? So entropy. So what happens as more and more plaintexts are encrypted using the same key, and how a successful ciphertext only attack can be carried out? So these questions can be answered in the form of entropy. So what is entropy? Loosely speaking, it's a mathematical measure of information, mathematical measure of information or uncertainty. Okay, computed as a function of a probability distribution. So okay, so suppose x bar is a discrete random variable. That means x bar consisting of a finite set x and a probability distribution defined on x. Okay, it's a discrete random variable which takes values from a finite set x, okay, according to a specified probability distribution. So it's a finite set x, so takes values from a finite set x according to a specified probability distribution. Right. So the question is, what is the information gained by the outcome of an experiment which takes place according to this probability distribution? This is a simple question. What is the information gained by the outcome of an experiment which takes place according to this probability distribution that is given to us? Or what is the uncertainty about the outcome? This quantity is known as entropy of x. We denote it by h of x. Okay. So what is the uncertainty, you know, about the outcome? So let me give a small example to motivate. Suppose x bar is toss of coin. We know that the probability distribution associated is the probability of heads is 1 and probability of tail is, sorry, half. And this is half of probability, right? So information or entropy of a coin toss entropy is 1 bit, right? Since we encode heads by 1 and tails by 0, right? It's just 1 bit. Similarly, entropy of n independent coin toss. N independent coin toss. Coin tosses actually is n. Okay. Since n coin tosses can be encoded by a bit string of length n. Okay. So here is a small example. Just take random variable x bar that takes three possible values. Suppose x1, x2, x3 with probability half, 1 by 4, 1 by 4. So suppose we encode the three possible outcomes as follows. X1 is encoded as 0, x2 as 1, 0, x3 as 1, 1, right? So then the weighted average number of bits is the encoding of x. So weighted average number of bits in this encoding of x bar is actually half into size here 1 plus 1 by 4 this probability times x2 has size 2 plus 1 by 4 into 2 is equal to 3 by 2. Okay. So that means we are getting some idea. So suppose an event which occurs with probability 1 over 2 raised power n could perhaps be encoded as a bit string of length n, right? So basically, if the probability is 1 over 2 raised power n, we can say that they can be encoded by bit string of length n. Okay. Length n. So more generally, we could imagine that outcome occurring with probability p p might be encoded by a bit string of length approximately log 2 base p. Okay. So when it is 1 over 2 raised power n, it's length n. So when it's probability p, this is the bit length. Okay, log 2 base p. Okay. So these ideas suggest that we can define the entropy of the random variable. So I'm just defining now. Suppose x bar is a discrete random variable that takes on values from a finite set x. Entropy of the random variable x bar is defined by hx bar minus summation x belongs to x, probability of x log base probability of x. This is the entropy of a random variable x. Okay. Now, certain observations or remark. We know that log 2 base y is undefined if y is equal to 0, right? Log of 0 is roughly minus infinity, right? So it's kind of undefined. So what we can say that, so basically entropy is sometimes defined to be the relevant sum over the all non-zero probabilities. However, since we know that limit y tends to 0, y log 2 base y is equal to 0, right? So this product is there actually. Because of this quantity, we also include 0. So there is no difficulty in allowing probability of x equal to 0 for some x, so we can actually still compute. And second thing is that base 2 is here we have used log base 2. If you use some other base, the the value of another base would only change the value of the entropy by a constant factor, right? So these are the two important things to observe. So now let me compute the entropy of a random variable now. If size of x is n, and suppose probability of x is 1 by n for every x in x, okay, then entropy of this random variable x is log base n. Second, entropy of x is non-negative for any random variable x bar, and hx is equal to 0 if and only if probability of x naught is equal to 1 for some x naught in x and is equal to 0 for all x not equal to x naught. Okay, so this is these are some general basic results about the entropy. So now, so we define entropy of a random variable. Now we know that our plain text can be treated as a random variable, our ciphertext can be treated as a random variable, our key space can be treated as a random variable. So that means we can compute the probabilities like h of k, h of p, and h of c, right? So how to compute these things? K is the random variable associated with key, p bar is the k bar, p bar is the random variable associated with plain text, c bar is the random variable associated with ciphertext. So let us take the same example that we have looked at earlier in earlier classes, that if p is equal to a comma b, probability of a is equal to 1 by 4, probability of b is equal to 3 by 4. Suppose key space consisting of 3 keys, k1, k2, k3, and then we have the probabilities associated with k1 equal to half, probability of k2 same thing as probability of k3 is equal to 1 by 4. A is equal to, sorry, C is equal to ciphertext is 1, 2, 3, 4, and our encoding matrix is A, B, K1, K2, K3, 1, 2, 2, 3, 3, 4, right? So once we have these things given to us, this is the plain text, key space, and the probability of plain text, probability distribution for plain text, probability distribution for key space, and ciphertext. We have computed the probability distribution for ciphertext in earlier examples, right? So now, for the plain text random variable, the probability will be, what is the probability here? Plain text is A and B, right? So for A, probability is 1 by 4. It is minus 1 by 4 times log 2 base 1 by 4. I'm just applying this formula. I'm just applying this formula here. Minus summation x belongs to x, probability of x, log 2 base, probability of x, right? So minus 1 by 4, log 2 base 1 by 4, minus for B, what will be? 3 by 4, log 2 base 3 by 4. Now if you simplify this, this turns out to be roughly 0.81. Okay. Similarly, you can compute for the key space, for the key random variable, this is 1.5, and for the ciphertext random variable, you have to compute this probability of ciphertext, which earlier we have done. It's equivalent to 1.85. Okay. Okay, so this is an example. Now look at certain properties of the entropies. I'll talk about what is known as Jensen's inequality. It's a very famous inequality. So let me use things there. Properties. So I'm going to obtain certain relationship between the properties of random variables. Then I will show you how this can be applied to ciphertext, plaintext, and and the key. The random variables of ciphertext, plaintext, and the key. So a function f is said to be a concave function. I'm talking about real valued function actually. Okay, concave function on the interval I if we have f of x plus y by 2 is at least f of x plus f of y divided by 2. And then we say that f is strictly concave function on I, some interval I, if this is a strict inequality. That is fx plus y by 2 is strictly greater than f of x plus f of y divided by 2 for all x and y in I. X is not equal to y, right? Now we can state the Jensen's inequality. I will not give you a proof, but at least you should have the idea of what is Jensen's inequality, because normally in calculations we use this quite often. Jensen's inequality. Suppose f is a continuous, strictly concave function on interval I. Suppose further that ai's are numbers such that their sum from a 1 to n is 1. These are positive numbers. 1 less than equal to 1 less. Then summation ai f of xi is less than equal to f of summation ai xi. This is the Jensen's inequality. I is equal to 1 to n. Summation I is equal to 1 to n. This is useful. Xi belongs to the interval I. 1 less than equal to I less than equal to n. Further equality holds in the Jensen's equality. Holds if and only if these xi's are same. Okay. Then the equality holds. So this is the Jensen's inequality. Actually, I'll show you, how to apply this in the calculations. Okay. Okay. Now, just note that log 2 of x is a strictly concave function. We'll be using this fact, concave function on interval 0, infinity. This is a fact that we are going to use. From the elementary calculus, you know this fact anyway. Okay, so now we are going to give you one main result. Suppose, so this is a theorem. Suppose x is a random variable. So discrete random variable having a probability distribution distribution that takes on the values P1, P2, Pn, Pi's are positive, 1 less than equal to I less than equal to n. Then entropy of the random variable x cannot exceed log of 2n. With equality, equality holds if and only if Pi is equal to 1 by n. 1 less than equal to I less than equal to n. Okay. So the proof is very simple. Using Jensen's inequality, we know that just compute the random variable entropy of the random variable by definition. Summation I is equal to 1 to n Pi log 2 base Pi, right? This is same thing as summation I is equal to 1 to n Pi log 2 base 1 over Pi. This minus, because of this minus, we are taking inside. So now we apply the Jensen's inequality on this summation. This will be less than or equal to log 2 base summation I is equal to 1 to n Pi into 1 over Pi. This quantity is 1. 1 plus 1 plus 1 summation n time is n. This whole thing is log 2 base n. We prove the things. And of course, you can see that equality holds if Pi is equal to 1 by n, right? So that I use. This is a simple application of Jensen's inequality, right? Now I can give you another important result. I think that will be last result for today. Is this theorem that the entropy of the joint random variables kind of thing is less than or equal to h of x plus h of y. Okay, with equality, if and only if x and y are independent random variables. This is a beautiful result, and we can prove it in a very nice manner. So let me do it for you. Suppose x bar is the random variable, takes on values xi. Okay, 1 less than equal to I less than equal to n. And y bar takes values yj. 1 less than equal to j less than equal to n. Now denote ti as probability. X bar takes the value xi, and of course I is between 1 and m, and suppose qj is probability that random variable y takes on the values yj. We define rij is the probability that x takes on values xi jointly and y takes on value yj, joint probability distribution. Okay, for 1 less than equal to I less than equal to m, and 1 less than equal to j less than equal to n. Okay. Now observe that Pi is nothing but summation Rij. J is equal to 1 to n. It's nothing but Pi. This is a simple observation. This is for 1 less than equal to I less than equal to m. And similarly, Qj is equal to summation over Rij. I is equal to 1 to m. And this is true for 1 less than equal to j less than equal to n. Right. So now with this preparation, I will look at the right hand side and I will compute hx plus hy. What is the value of hx plus hy? entropy of x plus entropy of y. With these notations in hand, so hx plus hy, entropy of random variable x plus entropy of random variable y is equal to minus, I'm just using the definition, I is equal to 1 to n, 1 to m, pi log 2 base pi plus summation j is equal to 1 to n qj log 2 base qj. Okay, so now I can substitute this pi and this qj, these values here, which we know. Okay, so in terms of rij, I will compute these values. This is nothing but minus summation I is equal to 1 to m, summation j is equal to 1 to n rij log 2 base pi. Okay, I've substituted the value of pi here, plus summation j is equal to 1 to n, summation I is equal to 1 to n rij log 2 base qj. Okay, I've just substituted this value of qj here and the value of pi here. Now what? So that means I can simplify this. This is double summation. I can take rij common. Summation I is equal to 1 to n. Summation j is equal to 1 to n rij. And this log a into b is equal to log a plus log b, right? So this is log 2 base pi into qj, right? This quantity. Okay. So this is the right hand side we have computed. Right side of this expression we have computed like this. Now we know, I will directly write down the expression for hx comma y, the joint probability, joint random variable you can say, and actually joint probability distribution kind of thing, and then we compute this difference. Let me compute this difference. So that hx comma y minus hx minus hy is equal to summation I is equal to 1 to m summation j is equal to 1 to n. I am writing the expression for this first. rij log 2 base 1 over rij. This is just by definition. Plus summation. Now I can write down the expression for this. Because of the negative sign, this will become plus I is equal to 1 to m summation j is equal to 1 to n rij log 2 base pi qj, right? So then I can again take summation rij common. See, this whole thing is summation I is equal to 1 to m summation j is equal to 1 to n rij log 2 base pi qj divided by rij. Now we apply Jensen's inequality. This is nothing but less than or equal to log 2 base summation over I summation over j pi qj. Okay, when this goes inside. Now this whole quantity is sum will be 1. This whole thing is log 2 base 1, which is 0. That means our condition is satisfied, right? That means we have this, that hxy is less than or equal to hx plus hy. Entropy of x over y, same thing as, is less than or equal to h of x plus h of y, because I have taken this the difference, and it turns out to be less than or equal to 0. Now, what about the equality? So there exist constants. There exist constant C such that Piqj divided by Rij is equal to C for every I comma j, right? This implies that summation over j, summation over I, Rij, same thing as summation over j, summation over I, Piqj. I can just sum. So basically, this quantity is 1. This implies that C is 1. So equality holds if and only if Rij is equal to Piqj. That is when probability of x bar is equal to xi, comma y bar is equal to yi. The same thing as probability of x bar is equal to xi times probability of y bar equal to yj. And this shows that x and y are independent random variables. Right. So this is all about this entropy, joint entropy we completed, right? So hxy is less than equal to hx plus hy with equality holds if and only if x and y are independent variables. I think that's all. I think in the next class I will talk about a little bit more, and then we are done with the basics, what is required to understand the cryptography. Then we can talk about the actual crypto systems. After that, we'll talk about especially DES, digital encryption standards, which was used quite often, which was started by IBM Lucifer cipher, and which was a standard industry standard. Later on, in 1999, AES, Advanced Encryption Standard, was designed, and that was used since then. So I'll talk about both of them. AES is based on finite field, so we'll discuss about those in probably this is class number 8 today. In class number 10th, we'll discuss about DES and AES, and maybe we'll start in the next class also a little bit. We'll see. Okay, how much is that? So there's some more, little bit more background is required, and then we are done with the background stuff. So we talked about the classical crypto systems. We talked about their attacks on the classical. So we done the cryptanalysis on them. Then we'll talk about the basics in terms of probability. We talk about the basics of the crypto systems, right? So that's all for today. We will see you in the next class. Okay. Thank you.
Thank you, sir.
Thank you.